Hello, my name is Ichiko Sugiyama, and I am a Chief Communication Officer at EAG, European Association of Geochemistry. And today we're kickstarting EAG Reactions webinar series. This is a first on a topic on academics in carbon dioxide removal, CDR projects. So before I start, I would like to quickly introduce to you about EAG. So EAG has, does many things. We organize conferences like Goldschmidt. We have open access journals. We have awards. We provide opportunities for outreach, mentoring, network, and science communications, as well as funding for early career scientists. And if you want to find more information about it, please go to this website and find out more. When you do go to that URL, you're taken to this particular banner, and there are many informations that you can actually find on this website and all the opportunities that EAG can provide. So today we have EAG Reactions on academics in carbon dioxide removal projects. And this is the first webinar series of EAG Reactions, and EAG Reactions is a series where experts, may that be academics or industry members, hello? Oh, sorry. Academics or industry members that can present their work, and which is followed by Q&A and open discussion. And today's topic is on academics in CDR projects. We have two speakers, Rebecca Tyne and Noah Planavsky, and each talk will last about 10 to 12 minutes, and we will start the webinar with Rebecca. I'm going to start sharing. Maybe Rebecca, you can share your screen now. I would like to do a quick introduction of Rebecca Tyne. Rebecca Tyne did her Ph.D. at Oxford University, and she was a postdoc at the Woods Hole Oceanographic Institution. She specializes in identifying and understanding the processes affecting subsurface CO2 storage, and she now works on using these to ensure subsurface durability. Today, she'll be giving a talk on her work at Isometric, which is a company that works on carbon removal standards and registry, as well as her work on CDR. Take it away, Rebecca.
Hi, thank you so much for having me here to talk today, and for everyone for coming. I thought I'd start off, although Chico has basically just said this, with a little bit about me. So I'm going to apologize that I have a cold and also technical issues today, so I apologize if anything goes wrong. But as Chico says, I got a PhD from Oxford looking at isotope tracing of crustal fluids, in particular looking at the behavior of carbon within the subsurface. I then went to Hui, where I met Chico, and continued to do very similar research. And it was there where I started working with Isometric, which is a carbon removal registry, where I work within subsurface storage, but also direct air capture. And then on Monday this week, I started at the University of Manchester as a research fellow. So it's been a very busy week for me. So I thought I'd start quickly with an outline of my talk. I'm going to give you a bit of a background into some of the research that I've done in CDR, well, in I guess CO2 storage and CDR, and then talk a bit about Isometric. I'll back up a bit and explain what the point of a registry is and what it is, because before working with them, I didn't know. And then talk about what verification looks like and the need for collaborative monitoring, reporting, and verification, and how academia fits into this. And then finally, I thought I'd highlight some open questions where academia could really help the CDR industry. So, a lot of my research today has been in understanding how CO2 behaves within the subsurface, as it directly impacts the durability. So this is just a schematic of the processes that could affect CO2 in the subsurface. At the bottom, we've got like the different trapping mechanisms or behaviors, and the process that takes place could affect its durability. For example, if we have precipitation, which is otherwise known as mineralization, this is much more durable than if you just have structural trapping. And you can see this in the little figure in the top right, which is originally from the IPCC report. This is just showing that how the different trapping mechanisms can affect the durability in the subsurface. Most of my research actually focused on biogeochemical cycling of carbon. So this generation of different biological gases from microbial consumption. And I did this using this biogeochemical toolkit from the table on the right. I feel like this is the place to explain all of this, but I think this has been really important going into more of a CDR industry of understanding different techniques that can be used to understand the processes, but also how the biogas formation, so I looked at like the methane formation from CO2 injection could then be impacted in other CDR pathways. For example, I've been working on bio-oil and biomass injection into geological formations, which obviously will produce biogas, and it's using the same kind of techniques that I learned during my PhD and first fellowship, and then applying this to monitoring within CDR. So I guess that's how I got into CDR and Isometric. So I just thought I would then explain what Isometric is. So Isometric is a carbon removal registry. The big question there is, what is a registry and why do they exist? Well, a key difference between carbon accounting and your own personal bank account is that the collective carbon budget is a global common goal, and we're all invested in the same climate mitigation targets. This means it's really important to keep track of the global carbon budget in a public account where everyone can see what's happening, and keep everyone else accountable. The main purpose of a registry is that it's a public ledger that anyone can see these transactions of carbon credits, where one credit is one verified ton of carbon removed from the atmosphere. On a registry, you can see who bought and owned the carbon credits, and most importantly, you can keep track of when those carbon credits have been used to offset a company's emissions, for example. When this happens, it's retired and it can't be sold again, which means that two companies cannot use the same ton of carbon removed against their offsets. So basically, what the aim of the company is to try and make sure that carbon removal is happening responsibly, basically. So something I really want to point out here is the word verified. And what does a verified credit mean? So part of being a registry is you get to set the bar that credits must meet in order to be listed on the registry. And this is where monitoring, reporting, and verification comes in, and where science and academia comes in. So for a credit to be listed on our registry, it means it must meet a set of requirements that we set out. And this is in order to make sure that they're of the highest quality and very trustworthy. Something I just also want to point out quickly is that a registry is not the same as a marketplace. We don't sell these credits, and we think that gives like less of a conflict of interest within the area. Instead, what we're doing is setting the bar for these credits to be issued, and we're coordinating for them to be verified with independent third parties, as well as keeping track of where they are used. So the typical verification process, it starts with us. So it starts with us creating these monitoring, reporting, verification protocols, which is outlining how carbon removal is quantified for a particular process. And it's essentially like the rule book of how you're doing CDR and how you're making sure that it's durable. A carbon dioxide supplier will then prepare a project design document which describes in detail what this specific project will do and how it will carry out its monitoring and ensure durability. They then have to provide this removal and monitoring data back to us. We then get an independent verification and validation body. This body will then check the project design document and the protocol and make sure that the project fits. This typically involves doing site visits, checking all the submitted documents, as well as redoing calculations that were done within any of the submitted documents. However, this is actually a bit more complicated than just this right now, as there is many things still to be figured out. For example, monitoring and reporting is not necessarily just done by CDR suppliers. It could be outsourced to academic institutions, to nonprofits, or even to for-profit monitoring companies. Another thing to highlight is that there's not one single actor in any of these spaces. There's multiple verification validation bodies, there's multiple MRV companies, there's obviously multiple academic institutes, and Isometric's role is to help facilitate this verification process across all of these different actors. One challenge that comes with having such a complex web is there's no standardized rulebook yet. And developing these rulebooks requires a lot of collaboration, and that will come on to in a minute. But having the standardized rulebook as soon as possible is really important to avoid any potential unintended consequences down the line and to prevent like rogue actors within the market or bogus credits, which is something we've seen before in the voluntary carbon market. So a big focus of the work that Isometric does is to create these, to hopefully create these good rulebooks or protocols and build trust within the market. So, sorry, our rulebooks and protocols are basically there in order to establish a scientifically rigorous framework for quantifying this carbon removal. And we do this through collaboration with academia and also with CDR suppliers to ensure that they are feasible and operational, because there's no point in having a protocol that's like incredibly rigorous, but so rigorous that no one could ever meet the standards of it. We also want to use these protocols to help advance science. So this is by encouraging the collection and open sharing of data beyond the minimum requirements for removal quantification, and also by identifying gaps where extra research could really improve the monitoring, reporting, and verification processes. And this all means working really closely with academia. So I quickly just want to walk through this typical process. This is with our ocean and alkalinity enhancement protocol. So to begin with, we initially draft the protocol in-house with reaching out to experts for areas where we have a bit of a knowledge gap. Once we've done this, we then send it out to 7 experts, I think, from different academic institutions for an early review, as well as to some CDR suppliers to make sure that this was feasible. It's basically kind of like a peer review process, but instead of having 2 or 3 people, we had 7 people, and we were also able to pay them for their time for doing this. We then, at the Ocean Sciences meeting the other week, hosted a consensus building workshop around the protocol, where we had a group of about 50 people from a diverse range of stakeholders. And this was a really useful process because there was lots of great ideas and thoughts that were shared there, and we're currently in the process of following up from them. Once these changes are going to be made, the protocol will then go into public consultation, where anyone online can comment on protocol. So yeah, and this is open for about 30 days. We expect to revisit the protocol at least every 2 years, and definitely if there's been any changes in the science behind the quantification of the carbon removal calculations. So I'm probably running a bit low on time, so I just thought I'd give you an update about what's next. So obviously I've started back at the University of Manchester this week, and I'll be looking more at subsurface carbon, looking at the rates of these different processes, in particular focusing on biogas formation and looking at analogues to see if we can use past records to predict future durability. But as part of my work in Isometric, we've also been identifying areas where academic partnerships would be really useful, and we already have some of these going. So some open areas that we've come up with while developing protocols so far are looking at the sensitivity of ocean models for uncertainty in ocean alkalinity enhancement, constraining the timing of atmospheric benefits and enhanced weathering, as well as like nutrient displacement as a result of CDR. So, for example, like biomass, injection and burial, and how taking this biomass could affect the nutrients elsewhere. So that's the end of my talk. And if you're interested in collaborating with Isometric, there's a QR code here to join our science network, or you can just reach out to us directly. So yeah, thank you. Thank you very much. And I'll hand over now to Noah.
Thank you so much, Rebecca. It was fantastic. But we're going to do a Q&A and discussion after the talks. So let me quickly introduce Noah. Noah is a professor in the Department of Earth and Planetary Sciences at Yale University, specializing in applying isotope geochemistry to better understand modern, ancient, and future biogeochemical cycles. In addition to his appointment at Yale, which is a lot of work already, he currently serves as a senior contributing scientist at Environmental Defense Fund and Cascade Climate, working to combat the climate crisis by mitigating anthropogenic carbon dioxide emissions through an enhanced rock weathering. So take it away, Noah. Thank you so much for coming.
Great. Well, thanks so much for the invite and for everyone from Europe being here on a Friday afternoon. Yeah, so what I wanted to do was walk through a specific example, walk through one example of a carbon dioxide removal project and highlight an example of where there's a industry and academic partnership from that. So as was introduced, I consider myself a biogeochemist. So as the joke goes, that if you're interested in biogeochemistry, it's just a matter of time before you get interested in wastewater systems, which are some of the locus of the most intense biogeochemical cycling that you can have. But before talking about wastewater, I think it is good, even though we had some of this from the previous talk, to just frame carbon dioxide removal as well. So the least controversial way to frame carbon dioxide removal is by talking about what it would mean in terms of global carbon budgets and in terms of emissions trajectories. So I think it's not controversial at this point to say that if we want to meet some very internationally agreed upon climate goals, not only do we have to move to net zero, but in most cases and in most likely scenarios, when you consider other greenhouse gases, have to also have negative emissions for sustained periods of time at a scale that is much, much larger than what we currently have. However, those carbon dioxide removal projects, as we heard from last scale, are of course have to operate in a specific marketplace, have to be financed, and that's where carbon dioxide removal can become very controversial and can, in many cases, do more harm than good. So in the best case for this, what we would ideally like to see for carbon dioxide removal is that it has to be measurable. It has to be something where we know exactly how much carbon we are removing. It also should be permanent. The potential to have carbon storage, where you have something where you have carbon removal for a short period of time, it's removed, but it's released after a change in say, land use practices, is something that can also inhibit the goals that we have for carbon dioxide removal. And of course, what we need to balance behind having something that is very measurable and something that is permanent is making sure that it is affordable in that as well. So what I want to do with this talk is try to walk through an example of a research project I've been doing, or exploring a type of carbon dioxide removal that I think fits these goals, where it is we can have a very good sense of how much carbon we're actually moving. Carbon dioxide removal is durable, and it's a process that is very affordable. So when we think about various ways to get durable carbon dioxide removal, one of the things that we're balancing is thinking about how much we need to build new infrastructure. The case example of that would be thinking about new pipelines, new larger industrial scale facilities for carbon dioxide removal, or how much we can tie into existing infrastructure, or how much we can utilize existing infrastructure for carbon dioxide removal projects. So in most cases, when people think about using existing infrastructure, the one that has been the most focus has been on how we can tap into farmlands. There's a tremendous amount of our surface that is covered by croplands at this point. And those can be used as ways to the infrastructure and the ability to have large amounts of mass transfer in those systems can be used to fuel efficient carbon dioxide removal. What is another major aspect of how we have transformed the landscape, how we've transformed the water cycle, is wastewater systems. And this is one that I feel like has gotten much less attention in the carbon dioxide removal space. It is one of the things that I always like to joke with people is what are the few things that people agree are positive aspects of civilization, things that without question just cause net good to society. And wastewater treatment plants are one of the few things that I think are generally agreed upon are a net benefit to society. Wastewater treatment plants, however, also have, besides their actual intended purpose, which is doing things like preventing spread of diseases like cholera and others, could be used to capture massive amounts of carbon dioxide removal in the system as well. And the basic idea behind this is very straightforward. So we move a massive amount of organic, we have spent trillions of dollars moving a massive amount of water and organic matter together to be processed. We are creating facilities at the end of our wastewater infrastructure that are designed to burn through as much organic matter through microbial remineralization as possible to create massive amounts of CO2. And so thousands of tons, tens of thousands of tons in many cases of CO2 is produced, of CO2 that was recently in the atmosphere, is produced in wastewater treatment plants through microbial remineralization every year. And also this process of remineralizing organic matter in wastewater treatment plants also creates other greenhouse gas emissions. Nitrous oxide and methane are emissions that come from wastewater treatment plants that we could think about also through carbon dioxide removal processes, potentially mitigating. So this combination of factors is what gets me very excited about thinking about how we can modify, how we can reimagine wastewater treatment plants to be centers of greenhouse gas reductions. So there are any number of ways to do this, to think about how we can transform the infrastructure that we have in wastewater treatment plants to something that drives carbon dioxide removal. I think one of the most straightforward ways, and one of the ways that drives durable carbon dioxide removal, is by thinking about these wastewater treatment plants as ideal settings for enhanced weathering. Ideal settings where you can take an alkaline mineral and combine that with acid to form cations and bicarbonate. And in most cases in wastewater treatment plants, those are directly discharged into a large aqueous body, and in many cases directly into the ocean, where that bicarbonate can be stored for long time periods. One of the benefits of thinking about wastewater treatment plants relative to agricultural settings is that any acid that is produced, meaning if you have strong acid from nitrification, or if you're thinking about it from carbonic acid, will be the equivalent of carbon dioxide removal from the atmosphere, because unlike soils, this is a single aqueous system instead of having the potential for strong acid interaction with solid phase aspects of the system, or having the counterfactual scenario in an agricultural setting, already removing that strong acid through a weathering reaction. So in other words, the simple idea of enhanced weathering in agricultural settings is that we have large amounts of acid that, if it doesn't interact with an alkaline feedstock, will directly drive CO2 emissions to the atmosphere. You can add an alkaline mineral to the system, and that will lead to very straightforward carbon dioxide removal that can be directly quantified because wastewater treatment plants are a closed system. Okay, so I can walk you through a case study here. And this is one that I'm doing with Crew Carbon, which is a company that was started by my former postdoc. I'm originally a geologist. Everybody loves a field photo. My field photos over the last couple of years have changed a little bit. Instead of being in some of the most beautiful settings looking at rocks, I've shifted more into being in what most folks do not consider some of the most beautiful settings, but that are engineering marvels. So this is an example, or a photo from a enhanced weathering deployment in the Greater New Haven Pollution Control Center. Yale is in New Haven. We've been working for the last couple years with the local wastewater treatment plant, which is shown from above here, in where the primary treatment step down to where you flow directly out into the ocean off the screen here. So one of the benefits of this, I already alluded to this, one of the things that is a real benefit of working in wastewater treatment plants is continuing the problem in other forms of enhanced weathering, is quantification. So in wastewater treatment plants, because it is a closed system, the quantification of the amount of weathering that you actually have is relatively straightforward. It is possible to, of course, track carbonate weathering, just removing the CO2 from the system, with multiple different aqueous measurements. You can directly measure the amount of calcium you have in the system, and you can directly measure the shifts in the carbonic acid in the system. You can also apply the same closed system aspect actually to the solid phase of wastewater treatment plants as well. And the solid phase aspect of wastewater treatment plants is closely regulated for obvious reasons, exactly the mass moving through. So you can actually check for the extent of calcite, of limestone dissolution that you have, not only by monitoring the aqueous phase in wastewater treatment plants, but also by looking in the solid phase for the amount of calcium carbonate that you have in the system as well. So in other words, it is possible in wastewater treatment plants to have multiple redundant, empirically based ways to quantify the amount of carbon dioxide removal you have. I think this makes that stand out is right now, I would argue, is one of the most straightforward ways to monitor a form of carbon dioxide removal. So in the actual deployment in Greater New Haven, so far over the last couple months have removed a little over 15 tons of carbon dioxide removal so far. Which puts it at a scale where it is definitely still a pilot scale, but is definitely moving beyond the benchtop and what typical academic trials are, the typical scale of academic trials. One of the other aspects this I alluded to in the beginning, one of the other aspects that excites me about this as well, is this process of carbon dioxide removal also has other potential benefits to the wastewater treatment plant. There are a bunch of aspects that probably would be less interested in how it can actually improve the actual wastewater treatment process. But one of the other benefits to the actual wastewater plants is that it can have a strong decrease. The modification of the pH in the system can lead to a strong decrease in nitrous oxide emissions. So it's an example showing some actual empirical results of nitrous oxide emissions, again from the New Haven plant here. And the basic idea from this is just both from the nitrification and the denitrification side, there's a well-established link between the pH of the system and the emissions. So when we think about management of agricultural lands, is the same idea. One of the ways to regulate nitrous oxide emissions in agricultural settings is to have better pH management in those systems. Okay, so then the obvious question is what does the life cycle look like for this process? So these results specifically for the Greater New Haven deployment again. And what you notice a relatively small amount of per ton of rock, a relatively small amount of the carbon dioxide removal actually is involved in the processing of the material that is added to the system and the transport of the material to the system. So when you think about it as this is especially given that this is pilot, something that's a not optimized amount of inefficiency in the process is something that is fairly effective, especially when you consider this to what would be large amounts of energy associated with, say, direct air capture or some of the more energy-intensive forms of ocean alkaline enhancement. And one of the real areas, as just a note, where you can have where you can improve this process is right now we're working with a milled material, but of course there's a massive amount of waste fine material that is possible to be used as the feedstock for the enhanced weathering that will make a difference in your life cycle assessment. Okay, so as the last question to end it up here is, it's great to have a pilot on a small scale. And one of the questions, and I think one of the things that my question is, regardless of the scale, wastewater treatment plants are going to be interesting because they are a case where we can have very high certainty of how much carbon we're actually removing. But one of the things you want to think about is what is the actual potential of this on a local, regional, and in a global scale. And I apologize, especially presenting in a European organization, not a US organization. This figure is in billions of gallons per day, which is how folks in the US think about wastewater treatment flows. But one of the things that stands out from this, and hopefully everybody knows roughly what a gallon is, there is a massive, massive amount of wastewater. It is difficult to think about it is difficult as it is such a large number. This is one of those that is difficult to actually quantify. So in the US, on the municipal side, there's roughly 55 billion gallons per day. In the industrial side, 82 billion gallons of wastewater produced per day. That is roughly 20% of the global wastewater flows. So a very large amount of water is flowing through trillions of dollars of infrastructure into closed systems where it is in closed CO2-rich systems. So we can estimate how much that would actually look like for carbon dioxide removal by thinking about either from a mineral saturation state with the average composition of wastewaters, or by thinking of a just amount of CO2 that is produced in these systems, how much we could remove. And the number, if you take it from this geochemical potential point of view, is very large. It is also very uncertain, and been working over the last couple of years of trying to reduce our uncertainty in this number. But I think what I can confidently say is, in any way you come up with this number, and any uncertainty that you have to this process, there is, from a geochemical point of view, the potential to have billions of tons of CO2 removal from wastewater every year, over 1 billion tons of CO2 from wastewater. I think it is very important, and one of the things that geochemists do not do a good job of separating is a geochemical potential is very different from an actual implementable potential. There's, of course, in most cases for carbon dioxide removal, the geochemical potential is not going to be what limits how much of this process we can actually have. It'll be socioeconomic factors. But that being said, there is, I think any way you slice it, there is a strong potential to have this be a process that is very impactful, both from regional carbon budgets into a global carbon budget when we think about the amount of carbon dioxide removal we are looking to achieve. Okay, well, I will leave it there, and I think I went over, sorry. But as one last plug, if you're interested in enhanced weathering, we are having a conference at Yale on April 26th and 27th that is free to attend, and would encourage everyone to check it out. The Saturday, the second day of it, will also be available for free online. And I will leave it there.
Thank you so much for the fantastic talks. Now we're moving to Q&A and discussion. This is a recorded talk, so if you are not comfortable asking the question in person, you can write in the chat and I can read them out loud. Or if you would like to actually directly ask the question and have a discussion, please unmute yourself and ask the question. Thank you. Anybody have any questions? Hello. Oh, yeah. Do you wanna do you wanna unmute yourself, Eva? And yeah, perfect.
Hi, good to see you. Thanks for your talk. Noah, I had a question about your wastewater treatment plants. How much resistance did you face when you talked to those people, and are there any negative outcomes of this? Any downsides?
Yeah, I mean, I think it's the same thing with when you're trying to do enhanced weathering in agricultural settings, and same thing with wastewater treatment plants. If you're try to think about what are the aspects that actually benefit them, and have it as something that is directly ties into their process as much as possible, and then it'll be appealing. So for the case for the Greater New Haven, one of the things is because it's discharging into coastal settings, they're very worried about their nitrogen load. And when you have a lower pH, your nitrification actually becomes sluggish, right? It's kind of just as how it works. So they were actually they were most excited about this, not from the greenhouse gas benefit side of things. They were interested in how they can meet their discharge permits and how they can have a free way of increasing nitrification rates, which are essential to have the denitrification step from it. So I think it's a case of for maybe kind of the way I think about carbon dioxide removal. If it's you're gonna have a hell of a time scaling if you're not helping your key stakeholders. For wastewater treatment plants, it's the actual folks that work there. For agricultural lands, it's the actual farmers.
And does it impact their sort of daily workflow much? Were they resistant in the beginning, or I guess how disruptive is this to them? Or
yeah, I mean, I think that really depends on the scale. I think that's one of the really interesting questions of where there has been some pushback is basically we would love I think most wastewater treatment plant operators would love free alkalinity. It can also help with particle aggregation to some extent, but if it's going to disrupt the process, there ends up being pushback there. Although the thing I would say is that in both farms and in wastewater treatment plants is they're designed to already have industrial processes happening. That's one of the benefits to it. That so the idea of trucks commonly coming into wastewater treatment plants is something that is not uncommon. For instance, in the New Haven one, there's a constant flow of trucks that are delivering from septic systems. So it's kind of it's very easy to tie into the existing kind of flow of traffic in the existing kind of industrial processes.
Cool, thanks.
I actually have a question for Rebecca. You talked about protocol development and the steps involved in it, right? So you have initial draft, and then you have 7 experts reviewing that protocol. I just went to an OSM meeting, like Ocean Science meeting, and I felt like CDR conference, sessions are a lot of people have a lot of disagreements, a lot of conflicts. People are not necessarily communicating from the industry to the academic side of things. There was a lot of arguments even during this one session that I attended. You're now asking 7 experts to actually make a recommendation on CDR companies with where MRV is very difficult to do for a lot of the projects that they're working in. How long does this process take to actually finalize a protocol development?
So for the OAU specifically, it was 7. We got them before the OSM meeting, and then we ran a consensus building workshop with, I think it was over 50 people in the room together to try and get agreement on some things.
Okay.
We're then currently working through all of the feedback at the moment. I can't personally say how long it's going to take. From some of the protocols I've taken, that I've been leading, they've been slightly less. There's been slightly less mixed feelings from many sides in them.
Of course.
So it's been a much quicker process. But from the consensus building workshop, it's then taken a couple of weeks to get through all the feedback. So this is the example I'm thinking of here is the enhanced weathering one. It then is currently under public consultation, so we're still soliciting feedback on that. And that is being reviewed, I think, this week and next week. This will eventually get certified, but it's open for comments at any point that we're able to read, and
that's really cool. You said every 2 years.
Continual updating thing, especially in some of these areas.
Yeah, that was my second question. Is like you said every 2 years, but then I'm guessing you're in communication with a lot of these people and okay, cool. That's what I
Yeah.
wanted to know.
Yeah, for
Okay.
example, we
Yeah.
released a biomass injection one before Christmas, and some of the information related to that has already been updated into like a version 1.1. The 2 years will be like, it definitely will become like a version 2, but there will be updates all along, unless if there is a big change in the science, there will be a version 2 before the 2 years.
Right. Awesome. Thank you. There are a few questions in the chats. Noah, did you answer some of them? Or maybe I will read it out loud and you can answer them here. So Julia said, you mentioned the pH of the system can strongly alter the NTO emissions in wastewater. Have you found an optimal pH for this, or is it micro dependent?
Yeah, great question, and tried to did a not so great explanation in the chat, but so I think we're not working from any pure cultures in this. We're only working with the most with the wastewater slurry, the mixed liquor, and which is a very diverse. Not surprisingly, a very diverse set of microbial consortia. But in general, I think it fits like a Michaelis-Menten type expression, where when you're at very low pH, you have a bigger effect, and then it kind of wanes. So you can imagine that's the best way to do it. When you're approaching a pH of 7, the effect becomes the difference becomes pretty muted. In most cases, though, we're actually trying to bring acidic wastewater streams up to something that is more neutral. So I think in a lot of the plants there will be this effect, but it is important to note that in many cases, especially if you already are closer to a pH of 7 or above a pH of 7, the effect will be pretty muted, even if from a calcium saturation state point of view, you are undersaturated. So it does seem to be more directly tied, which mechanistically, of course, makes sense, to the pH of the system, not the carbonate saturation state of the system.
So there's a second question from Manuel from CSIC Spain to Noah. I may not fully have gotten the experimental setup, but it seems to me that limestone was added to neutralize acidity in the wastewater. So why is taking CO2 from a safe permanent storage limestone and dissolving and thus mobilizing it a method of CDR? It seems contradictory, but maybe I have missed something.
Yeah, great question. I could have been more clear about that. Well, first of all, you can think about this from any alkaline. You can think about this from any number of feedstocks. The process can be somewhat feedstock agnostic, but limestone weathering can be carbon negative or carbon positive. So if you think about just the forward reaction, and this applies also to agricultural settings, you're going to have a cation, calcium introduced into the system, and then that's going to be charge balanced by two moles of bicarbonate. So one of those is going to be derived from the actual carbonate. The carbonate ion will be converted to a bicarbonate. But the other one is actually going to be from carbonic acid. So it's unlike when you think about it from a silicate point of view, you are introducing a divalent cation in the system, and then you charge balancing that with two new what would be the negative bicarbonate ions. Where liming or limestone weathering becomes carbon positive is not because of the forward reaction from it. It's actually depending on the pH of the system, the 2 moles of bicarbonate that you have will then re-equilibrate and will be released as CO2, carbonic acid, and then the carbonic acid will re-equilibrate with the atmosphere. So the actual forward weather, and the simpler way, that was maybe the simpler way to state that was actually the weathering process of carbonates, whether it's in ag settings, whether it's wastewater, is actually carbon negative. You're introducing a cation in the system, that's going to be charge balanced. But in agricultural settings, where the cation can then be removed onto a Zorb fraction, that process can be turned into being carbon positive. That's why the IPCC lists liming as carbon positive, for instance. I think that's actually a simplification of what happens in agricultural settings and something I would love to talk about more. But in wastewater systems where it's an aqueous system and you know the pH of the system, it is very straightforward to have it just be a capture side. Good question, though.
Is there any other questions, soul burning questions that people want to ask? You can unmute yourself if you want. If not, meanwhile, I have a question. After working for both of you, actually, after working for CDR or working with CDR companies, how optimistic are you about the because we need to remove something like gigatons of CO2 per year to limit the global warming to 1.5 degrees. Are you guys both optimistic, or you became more pessimistic about the goal?
Well, I actually I like to think I thought the sponge paper that the work on trying to establish our real baseline that came out recently, I think was very interesting. I think we've already blown past 1.5 by some measures.
Yeah,
so.
yeah. I know.
So if you're asking my optimism on
I know,
1.5,
but
I can confidently say
but
it is.
yeah,
It
I
is
guess
very
two
low.
now. Yeah.
But that was not the question, I guess.
Yeah.
I think yeah, I mean, I think right now it's like I would think this is gonna would love to hear your answer on this as well, does. But as my take from it is that I think I am very optimistic that there is excitement and there is a lot of a large promising number of ways in which we can remove carbon dioxide. But what I'm most worried about is that we're actually, and if you look at what has happened in the voluntary carbon marketplace over the past 2 decades, there's been too much of a push to focus on scaling up before we know exactly what we're doing, and not enough of a focus on quality. Carbon dioxide removal, I think we also shouldn't kid ourselves. If you have carbon dioxide removal projects that are not well quantified, you have done more harm than good. And especially if they're in something that is a compensatory claim and is an offtake system. So I think there is a tremendous potential to do that. And I think what the next couple years, not even the next 10 years, I think really over the next kind of 5 years, we'll see if we can put in structures in place, have a focus on establishing good standards that allow us to have healthy growth of the system and not have hype cycles that collapse, or whether there's going to be money flowing into things, people rushing, people getting too excited, and then having backlash from that instead of putting science and quantification first.
Right. Rebecca, you have.
I very much mirror Noah's opinion on this. Like, it's a very exciting time of the fact that there's so many people trying to do this, and there's coming up with so many different ways in which CDR could happen. I'm cautiously optimistic that they're going to do it properly, but that is really where we need to do the work to make sure that it is happening properly. And yeah, it's not just a hype that's going to fail. And it's not something, we want to be careful that we're not doing CDR at the expense of something else as well. And I think that's something that does worry me occasionally.
Right. No, I agree with you. Bob Hilton, would you like to ask a question?
Yes, I would. Thank you. Thank you for organizing this. Great, really nice hearing the talks. I've got a question actually for both of you. It's the same question about this verification side of things. And I guess from kind of thinking of Noah's point about, where can we actually verify this with robustness and certainty, and what kind of measures we can make. But I guess there's, for any of these technologies, I'm thinking of kind of enhanced weathering, I guess, because I've thought about it most, but to roll out, there's that balance between what could you measure continuously to prove sequestration versus an acceptance that we have verified this amount of carbon will be sequestered following this protocol, and therefore you only need kind of spot checks, I guess, on verification. And then linked to that, the complexity of the verification method. So as geochemists, we can come up with lots of clever ways, we think, to quantify these things. But actually, if it comes down to just the measuring conductivity, how do we deal with the needs for verification across the registry and from the kind of users, and also that the use of geochemistry, like some of the complicated tools we could use, radiocarbon, lithium isotopes, things like this.
Yeah, I can take a first go, Rebecca.
Awesome.
Yeah, I think so for enhanced weathering specifically, I think the part of it's going to be that there's first of all, we're going to any effort on verification is going to fail if we don't have data transparency. If we don't have full data transparency and nobody knows what the hell people are making claims on, we are going to, without question, fail. So the easiest thing that we should all be pushing for in that, I think, is having that first and foremost of every discussion on this process. I think it's also going to be, if we put this in one sector, one group's bucket, we are also going to, without question, fail. So for enhanced weathering, there are some things that suppliers are going to, carbon dioxide removal companies are going to be able to do things that academics are just never going to be able to do at scale. Having done a bunch of enhanced weathering trials, I can say that from the academic side, and having worked with companies to do that, I can say that academics are really good at losing money. That's kind of our job. Like really poorly doing logistics is kind of my job. So there's some aspects that, you need companies to be involved in the early stages of these things. There are ethical questions from that, but I think if we just think about what the hell, are we going to be in a position 3 years from now where we know what's actually happening? Companies are going to play an essential role from that. Academics also, I think, don't have to convince anybody in this call, in this audience, that academics are going to play an essential role. But there's also, for enhanced weathering, I think the scale where it's been lacking and where I think we need to do a better job is you need measurements at the field scale. Those need to be open, but you also, as things are scaling up, need measurements at the catchment scale and need more measurements at kind of the whole river scale. And we need to be thinking about what are safe guardrails for deployments where we'll actually see emergent signals in systems. And the US used to have an amazing river monitoring network. I would argue the best in the for my second most American thing of the day, the best in the world, besides my billions of gallons. And that is not receiving the same level of funding that it used to be. Ideally, if we want to really have a good sense, again, 5 years from now, 10 years from now, of how efficient this really is and what are the risks, we need to have academics being well-funded, forcing companies to be transparent, and ensuring that there are things that happen best at the federal and state level, like the river monitoring network that the US used to have.
Rebecca, you wanna take over now?
Yeah, I was just going to say that I totally agree that getting access to data from these companies is going to be so beneficial in advancing our understanding and knowledge of the processes, but also how best to then verify going forward as well. I can't actually say too much about verification to do with enhanced weathering. I've mostly been on subsurface projects, but in doing this, we also Bob knows I'm a geochemist, and he knows what kind of isotopes they do. And I have been for protocols I've written things that need to be measured essentially, and then things that are strongly recommended to be measured in order to try and get the most amount of measurements possible in these early stages, again, just to build up our knowledge in the area and really understand what's happening, to make it easier going forward.
Oh, Jodis, would you like to unmute yourself and ask the question?
Yeah, hi. So I'm Yotis. I'm an assistant professor in Durham, here in the UK. A question for both of you, I guess. As academics, when you work, Noah has mentioned this a little bit, that the sort of ethical issues, when you work with companies, that are, they need to make a profit, right? Especially if it's maybe easier with the wastewater, where there's sort of co-benefits, and they have sort of slightly different incentives, or main incentives. But if it's, startups whose business model is, really based on selling the carbon credits as soon as possible, right? And you, an academic, collaborating with them, how do you handle that sort of conflict of interest? And do you feel like that's an easy thing to get around or challenging? Yeah,
I think it's a great question, and say that it's a question that everybody has to wrestle with their own way. There's not a right answer to it. The way I've personally chosen to deal with it is to, I think financial incentives are really important. So I've chosen to not take any equity and not be paid by companies. My business plan as an academic is to just never be paid and continue losing money. So that I think is the financial that made it easier for me on conflicts. So I have certain biases and conflicts. Like I want to only work with companies that are going to be transparent on their data. I want to only work on companies that are making empirical measurements at this stage behind any sort of claims they have. But even with that, I think there are certain real hurdles to working with companies. Every company is thinking about how they will not design themselves to be obsolete. And that's the exact opposite of how we think about things as academics, where you're trying to make yourself obsolete as quickly as possible, trying to solve a problem, and then you can move on to something else. So it is a very different framework, and I think but the short answer for me is basically that if companies are fully transparent, and if I'm not standing to make money from the process, I don't feel like I have a strong conflict from it.
Cool. Yeah, thanks.
I guess for me, like, I'm not involved in anything commercial when I work with Isometric. I advise on the science part of it. This also doesn't impact any of the research that I do. So although I suggest to do measurements like what I have done in the past, but none of my research is like directly impacting what Isometric are doing or anything like that. So it does feel like I have two very different hats when I look at things. And I'm not involved in any business development or anything, which is nice. I'm definitely a scientist.
Is there any other questions, comments? If you're too shy to ask questions, please write it in the chat. If not, it's already 10 a.m. here in the East Coast. Thank you so much for coming to this first EAG Reaction webinar event. I really enjoyed it. It was awesome. Thank you so much, Noah and Rebecca, for coming and giving us awesome presentation, and everybody for asking very interesting questions. Thank you very much. And I am hoping to take this recording and put it up on YouTube so that other people can actually view the webinar, as well as I might write a short blurb summary of what happened today. So keep an eye out. So thank you so much. Yeah, we will have more webinars in the future. So thank you so much, and keep an eye out on Twitter and other social media platforms on EAG. Thank you so much. Bye.